Yesterday, somebody asked, with these sort of integrals that we're doing that involve these inverse trigonometric functions, will we sometimes have definite integrals? And my answer was absolutely. So here we go. We want the integral from 0 to the square root of 2 of 1 over the square root of 4 minus x squared. Does that integral of 1 over the square root of 4 minus x squared fit into one of our trig patterns? Yes, that's arc sine. So this is going to be arc sine of x over 2, I believe, because a is 2 squared, which gives 4. And then we plug in our numbers, 0 square root of 2. So we have the arc sine of the square root of 2 over 2 minus the arc sine of 0. Arc sine of the square root of 2 over 2 is... I heard a right answer, and I heard a right answer, but in the wrong units. Pi over 4. We never use degrees in calculus. Minus the arc sine of 0. 0. So our answer is pi over 4. Alright, so that one wasn't so bad. It must get worse, right? How about the integral? From 1 to 4 of 1 over x times the square root of 16x squared minus 5 dx. Does that one fit into one of our inverse trig patterns? Yes, it does. It fits into arc secant almost. The problem with this one is we can't have a 16 right there, so we do have to do a u substitution. So what's our u substitution? U equals 4x. So du is 4 dx. And then what am I going to do with this x right here? I'm going to solve. So x is u over 4. And because of this 4 here, I need a 4 there and a 1/4 out there. Okay, so this becomes the integral, 1/4, the integral, 1 over u over 4 square root of u squared minus 5 du. And then, of course, we need to change our bounds. 4 and 16. Because when I plug 1 in here, 4 times 1 is 4. When I plug 4 in, 4 times 4 is 16. 4 and 16. Now, this always works out that this 1/4 on bottom reduces with that 1/4 on top. When you do this kind of u substitution, that should always happen. Those constants should always knock each other out, which is helpful. Okay, so we get, this falls into our arc secant pattern, correct? And our arc secant pattern had a 1 over a out front. What's a? A is square root of 5. Because square root of 5 squared gives me 5. So this is 1 over the square root of 5 arc secant of u over a, so it's u over the square root of 5. And then we got to plug in our numbers, 4 and 16. Okay, plug in my numbers. 1 over the square root of 5 arc secant of 16 over the square root of 5 minus 1 over square root of 5 arc secant of 4 over the square root of 5. What's the arc secant of 16 over the square root of 5? Yeah, I don't know either. And how about the arc secant of 4 over the square root of 5? Yeah, I don't know that one either. So what am I going to do? Well done, there's my answer. So that's going to happen with a lot of these problems. A lot of these, sometimes you'll get lucky, like the first problem we did, and you'll get arc something of an angle that you know, and it'll work out. Most of the time, you're not. You're going to end up with ugly numbers. I don't know the arc secant of 16 over the square root of 5, so I leave it just like that.
On the last one, can we leave it just the way it was?
Oh no, if you can give me a nice answer like pi over 4, I'd like to see a nice answer like pi over 4. That's one you should know. Okay, so that one I would expect to see pi over 4. But this one, there it is, I leave it just like that. Other questions on that? Okay, the last thing that shows up in this section is something called completing the square. And problems where you complete the square are going to look like this. You're going to have the integral of dx over x squared plus 4x plus 13. The way that stands, does that fit into any of our patterns? No, it looks closest to the arc tangent pattern, but the arc tangent just has x squared plus a number, doesn't it? This x in the middle is a problem. That doesn't fit into our arc tangent pattern.
There will be 2 dx's in these.
Oh no,
Throw me off.
there's a bonus dx there. Bonus dx, just one. All right, so this one looks like arc tangent. If that 4x were not there, then that could fit into an arc tangent pattern. When you see something like that, when you have something on bottom that almost fits into the right pattern, but you've got this extra term, that tells you need to complete the square. Okay, so I'm going to come off to the side here. And I'm going to write x squared plus 4x plus 13 equals, what do you remember about completing the square? Yeah, typically when you have an equation, if you're solving a quadratic equation by completing the square, you're right, you would subtract the 13 to the other side, and then you would do what you said. But we don't have an equation here, so we're just going to leave the 13 right there for now. But the important thing is we take x squared plus 4x, and then we add a number. So we're going to add a number, and to balance it out, we'll have the plus 13. We'll subtract that same number. So in essence, we add a number and subtract a number, so we're adding 0. We're adding 0. All right, so how do you figure out that number you're supposed to add? You take the middle term, which is the middle coefficient, which is a 4. You divide it by 2, and then you square it. So that happens to be the number 4. So we're going to add the number 4 and subtract the number 4. How does that help? Why is this called completing the square? What can you tell me about x squared plus 4x plus 4? It factors in a very special way. It's x plus 2 times x plus 2, or even better, we write it as x plus 2 squared. And then we combine the other two numbers. 13 minus 4 is 9. Okay, so we come back here now, and we rewrite. We have the integral of dx over x plus 2 squared plus 9. How did that help? are now in the form of something squared plus a number. That's my arctan form. So this is technically a u substitution where u is going to be x plus 2. And that works out wonderfully because du would be dx. So technically that's a u substitution, but I'm not going to bother writing that out. It fits exactly into the arctan formula. So we're going to have 1 over a. In this case, a is a number 3. Arctan of u is x plus 2 over 3 plus c. Questions on that one? How about the integral of 2 over the square root of minus x squared plus 4x dx. Once again, does that fit into any of our patterns? No. Which pattern is it closest to? Arc sine? Why do you pick arc sine? It's right, by the way. What's that?
It's not negative.
No.
That's closest to the rule.
It's closest to the rule. If there were an x on the outside of the square root, then I'd be looking at arc secant. If there was no square root, then I'd be looking at arc tangent. So the one that has a square root on bottom and does not have an x on the outside, that's arc sine. So that looks closest to arc sine. Okay, so we need to complete the square. So we have minus x squared plus 4x. How do you complete the square on that one? Okay, the problem with this one is in order to complete the square, this first coefficient, this leading coefficient, has to be the number 1. It's not the number 1, it's the number -1. So what we have to do is we have to write this polynomial as -1 times x squared minus 4x. You've got to factor that -1 out. Or if it were any other number, before you could complete the square, you've got to factor that number out. So we're going to write this as -1 times x squared minus 4x plus my special number. So what's my special number this time? 4 again, because I take -4, I divide it by 2, -4 divided by 2 is -2, -2 squared is 4. So I got to add a 4 right there. So there's my plus 4. And then I have to balance it out here. So what number do I put outside my brackets? A -4. And that would be the common mistake. Plus 4. If I'm doing a plus 4, why do I do another plus 4 to balance it? Because that whole thing is multiplied by -1. When I put a plus 4 inside this parenthesis, I actually added a -4. So I have a -4 here, which means I need to balance it with a positive 4 there. So that, watch out for those. Those are tricky. It's easy to put a plus 4 here and then do a -4 there. But you can remember, get a minus outside here. Okay, so this factors as -1 times x minus 2 squared plus 4. So I'm going to come back here and I'm going to rewrite this. This is the integral of 2 over the square root. I'm going to write this as 4 minus x minus 2 squared. So I took the thing where I had completed the square and I reversed the order on it. Why did I reverse the order? Why did I write it as 4 minus x minus 2 squared? Because that's the way we usually write our arc sine formula. Our arc sine usually has a squared minus x squared. So once again, technically this is a little u substitution. U is going to be x minus 2. Again, it works out great that du is dx. Final answer, looks like we've got the 2. We're going to have arc sine of x minus 2 over a, what a is 2, plus c. The negative one, when I rewrote it as 4 minus x minus 2, the negative 1 is right there. Put the negative 1 in if you want. There's the 1. Sneak it in there. Other questions?
If that had not been a negative 1 out front, or it had been a larger number, we would have had to do something different. I forget.
Okay. I don't see any of those in the book. I was looking for one, but I'll make one up. So what he's saying is, imagine, if you will, if you had the integral of dx over, let's say you had 3x squared minus 6x plus 8, maybe. I just made that up, so I hope the numbers come out halfway decent. I have no idea. Once again, I would look at this and I would say, well, it's most closely the arc tangent formula. If I did not have that 6x there, then it would be arctan directly. I could pull that 3 out and I'd be done. So that tells me I need to complete the square, and it's going to fit the arctan formula. So I'm going to have 3x squared minus 6x plus 8. And it's really the same deal as the last problem. In order for completing the square to work, this number right here has to be a 1. But it's not, it's a 3. So what I'm going to do is I'm going to factor that out of the first 2 pieces. So I'm going to write this as 3 times x squared minus 2x plus 8. I only factored out of the first 2 pieces because it's only the first 2 pieces that I need to use in order to complete my square. No, I can't take the 8 right out, because remember when we get done we need x squared plus a squared. So I need that number 8. I'm going to need it for my inverse trig form when I get done. Okay, so 3 times x squared minus 2x plus, the magic number this time is 1, because I take negative 2 divided by 2, that's negative 1. Negative 1 squared is 1. Plus 8 minus 3. Same deal. Because this 1 is inside the parentheses, I really added 3 times 1, which is 3. Just like we had with the minus sign a minute ago. So since I added a 3 here, I'm going to subtract a 3 there to balance it out. Alright, so 3 times x minus 1 squared plus 5. I'm going to rewrite my integral. This is integral dx over 3 times x minus 1 squared plus 5. Now we're very close to the arctan form, but we still don't have the arctan form. Why do I say that? I've got this coefficient right here. To be in the arctan form, I need just the thing squared, no coefficient there. So what am I going to do with that? Close. Well, if I multiply the 5 by 3, I would also have to divide the 5 by a 3, wouldn't I?
Should that be one?
Right. So I'm going to take this 5, I'm going to multiply it by 3 and divide by 3. And then I can factor this 3 out. But remember, this 3 is on bottom, so when I factor it out, it's going to be a 1/3, which I think is what you said. Yep. You're right. We got to rewrite this as 1/3 integral dx over x minus 1 squared plus 5/3. And now finally we have it in the arctan form. Again, technically it's a little u substitution. U is x minus 1. Works out perfectly again. du is dx. So I don't need to worry about any little numbers. So I'm going to have a 1/3. And then I'm going to have 1 over a. A is square root of 5/3. Arctangent of x minus 1 divided by a, so divided by the square root of 5/3 plus c.
When we pulled out that 1/3, what did we actually do to get the 1/3?
What we actually did is we took the number 5 and we multiplied it top and bottom by 3. And the reason we multiply top and bottom by 3 is that gives us a 3 here and a 3 there, and then we can factor out the 3. So that's kind of a weird number trick that you have to do every now and then. You take the number 5, you multiply it and divide it by the right thing so that you can factor, so that you don't have a number sitting out front of here anymore.
Why is it square root of 5/3?
Because remember, this number 5/3 is a squared.
Um,
So a, this formula has a here and a there. A would be the square root of 5/3. Other questions?
When you have a number in the numerator, you just bring it to the, bring it all the way down into the answer, because it's kind of like,
Correct. If I had a number in the numerator here, if I had a 7 up here from the beginning, then I could just take that 7 and bring it out front, and that 7 would just carry down everywhere. So having numbers in the numerator is not a bad thing. It's numbers in the denominator that mess you up and make you have to do more work. Other questions?